So go ahead and start with this. The first one we're going to graph will be a cosecant function. But in order to do that, we're going to utilize, to your benefit, the information that you know already about the sine function. So I'm going to do everything as if I'm graphing the sine function. But with the real intent of making this the graph of the cosecant. This is the final goal here. To get there, though, we're going to act like we're we are going to be graphing these sine functions. So let's draw this down, and then after that, draw your 3 horizontal lines in order to get ready for, and then your 9 tick marks to get ready for drawing the actual cosecant function. So we have these 9 tick marks, and we're going to be graphing the sine theta function. Now, one of the one of the things I love about the parent function with the sine is that it's simple in finding the oscillation and the amplitude, because oscillation, being that it's not present, makes it the identity property 0, and then the amplitude's 1. So just at the highest, it's going to go 1 and -1. Oops, it should be -1 down here. At that end, the negative. And then the period, y'all remember that with the frequency was 1. That was important because when we discovered or used the period, that'll be 2 pi over f, which meant that we're doing 2 pi over 1, which meant that it was just 2 pi. That would be my cycle. And the most important part that I need to take from that is just that the scaling portion of it was really my period divided by 4, which meant that I was dealing with 2 pi over 4, or better, reduced form pi over 2. This is not new because we did this in the as a first example when we first started graphing these trig functions. That was our very first thing we graphed with the sine, with just a sine parent function, doing these same techniques, going a little bit more involved in the oscillation and amplitude, but pretty much the same idea. So if you need a reference back, feel free to do so. We're going to now scale our actual graph by 0. This becomes pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2, and the finale being 8 pi over 2. So we have all our scaling done. All we're really needing to do now is just graph our sine trig function. So that's lovely because we know the pattern. We know exactly what to do. One of the things that I do want you to do is that we're going to graph it, but we're going to actually use a dashed line. We're not going to use like a solid line. The reason being is that I'm going to just use the sine function. Now, if y'all remember from the sine function, we start midline, and then it reaches its highest point at pi over 2. And then from there, it goes down to its lowest point, and then goes back to 0. Now, draw it as a dashed line. The reason why I want you to draw a dash is because we're just going to use it. It actually doesn't really, it represents the cosecant graph, but in a special way. Okay. This is lovely. Now, one of the things that we safely know is that the sine function, like if I ask you for the sine of a theta, you would tell me, oh, that's y. The cosecant, I would say that you may know that it's 1 over y. You probably have it written down somewhere, and that's how you originated. My focus is going to be with the secant now, the cosecant. And in order to graph the cosecant function, I am going to refer to the unit circle, because you know how we started with graphing the sine function with the unit circle? It's going to be at the same place. It's going to give me the direction to safely graph a cosecant function. what it's going to require is that when I pull up my unit circle, let me make sure I'm there. You go. All right. I want to point out. Oh, hold on. I captured it instead of clearing it. Okay. I want to point out something that that you know, that is that when we started with the sine function, like if I had asked you, hey, find the function or find the value of sine at 0 degrees, what would you all tell me that is the answer for that? It would be 0, right? Because you looked at the y value, correct? Okay. What about if I ask you, what is the cosecant of 0 degrees? What would be that? Yeah, it'll be 1 over 0, which you just said it right now, undefined. It would, and we had this experience with the tangent function, and we said it shows up in the graph as an asymptote. Do y'all remember how we had asymptotes on the tangent? So the same thing's going to happen at the sine function, but it's going to happen right at the starting point, right at 0. That's going to be, so our first asymptote is actually going to happen, hold on, not to here, where'd it go? Oh, it's here. I took this by accident, hold on. No, it's here, somewhere. Oh, here it is, okay. So our actual asymptote is going to occur here. So we're going to have an asymptote at 0. And now look at this. Look at the midline of the sine function. You see how it's at 0 right here? Okay, because that's the value at 0. The next asymptote that it's going to happen, that's going to generate, it's actually going to be at pi. And by showing you the unit circle, if I ask you the sine of 180 degrees, you would tell me, oh yes, Mr. Sandoval, that's 0 because of that value. So the same thing's going to happen. When I take the cosecant of 180 degrees, I'm going to get this undefined. So if you're able to understand that portion, that I'm going to generate another undefined, that means that everywhere that you see that this sine function is going to hit 0, there's going to be an asymptote that gets generated. Does everybody see where I'm placing these asymptotes at? I'm only placing them where sine equals 0. And that's because it's at those points that when you do 1 divided by 0, it actually becomes undefined. We are generating an error in math. Yeah. So here's another one, and here's another one. So cosecant actually generates a lot of asymptotes, isn't it? That's the first most important part to understand. That's kind of like the add-on that is new to us, is that we're going to have these asymptotes. Now, the other thing that's going to happen is that y'all understand that the cosecant is kind of like the reciprocal of the sine function, which is kind of like the inverse. Which, think about this. You know, you see how this one, we graph it by going down? Okay, if I go ahead and reflect it off its maximum, in reality, now it's going to look like this. In essence, what I'm doing is taking the inverse of that function, just in a special way. So it's going to happen there. It's going to happen here. It's going to occur here, and as well as here. So everybody see that? So that's exactly what's going to happen. Now we're going to have these. The cosecant is going to be an inverse function, and it displays itself in this manner. And where now we're going to have these graphs that are inverse at the maximum and following these asymptotes. So those are the two new add-ons. The two new add-ons is that now we're going to have asymptotes and this characteristic that they're going to inverse. Okay, so not anything that's really hard. We actually you have the benefit of knowing most of everything. So hey, everything else, when it comes to amplifying the frequency, the starting point, you're going to do that all the same. You're still going to apply like a different starting value, a different amplitude, just like you've been doing so far. The only thing that's going to be changed now is the fact that now you got to draw these asymptotes and inverse the function. That make sense for everybody? Okay, so now let's do a cosine. And the reason why I want to do a cosine and a tangent is that when we do this at home, or when you do it at home, I want something that you all can reference back to. Okay, when you do f of x, we're going to graph this one first with the real intention of using it to graph my secant. I'm I'm going to do the setup for graphing, which is the 3 horizontal lines, along with my 9 tick marks. Now, one of the things I love about the cosine is that as far as the scaling and the period, it's exactly the same as the sine function, which means that, first of all, we still have the benefit of using 0, 1, and -1 because of the way the amplitude and the oscillation works with the parent function. And we're going to have the same scaling because we're still dealing with the same period. So 0, pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, the 5 pi over 2, 6 pi over 2, 7 pi over 2, and then 8 pi over 2. So we have the, we know that we just proved that in our previous example. That's been proven as far as the scaling portion of it. The thing that's different about the cosine is the way that it generates itself. We all told ourselves or knew that cosine will start at the maximum. At 0, it was actually the value 1, its highest value. And it would then hit 0, hit its lowest value, go back to 0, and then go back to its highest value. So dash this line because, again, we're only going to use this for graphing the secant. So here, here, and here, and here. Same thing, dash as well. In solving these, one of the guarantees I had is that the cosine theta was equal to x. And now, so this was equal to x, and the secant data was 1 over x. The reason why I'm bringing this up is because I'm now going to examine this at values of when, like in this case, the first one I'm going to examine is not at 0, but actually I'm going to be real important is at pi over 2. At pi over 2, when I look at the x value, like if I ask you to find out the, let me clear this up. But when you look at pi over 2 and I ask you, you know what, give me the answer for cosine of pi over 2. Most of y'all will tell me it's the value 0, which is this one. So when I try to find the secant of pi over 2, I'm going to actually get 1 over 0. And this also means that wherever you see this cosine cross the midline, which is the value of 0, that's the places where generate an asymptote because of that actually inconsistency. That it's kind of not a mistake, but just something that we can't define, which means that in our graph, you see right here, see how this is the cosine is crossing at 0? It's going to be at this place where we're going to have our first asymptote. And then we'll have another one right over here, wherever it crosses 0. And then here as well, and here as well. So we're going to have these asymptotes that get generated because of these errors that happen. Yes? Those happen because at the time that I try to take, like if I take the cosine of pi over 2, which is at 90 degrees, which is this value here, and you know how this value is 0 and 1? The cosine is the x value, which means it's 0. When I try to take the secant, though, but that's not the reason I put an asymptote. It actually happens because when I try to take the secant of pi over 2, it's 1 over x, which means it'll be 1 over 0. And 1 over 0 is when we have an asymptote in our graph. That's how it's represented in a graph. So everywhere that you see the cosine function actually hitting this midline, which represents 0, those are the places that we have an asymptote that generates. And because of the way that it's an inverse, now instead of going down, it's going to head up like this. This is going to have this kind of feature to it. This is going to do this. They're all just going to change directions in the way that they demonstrate or result in. That's the effect. The cause being the secant trig. All right. Now we're going to do our last one, which is the tangent. Now with the tangent, we're actually going to go ahead and graph the or do the cotangent. Better put. Let's go ahead and then let me write down f of x of tangent of x. And our real goal is to actually graph the cotangent of x. I would say that this is the only trig function in where the use of the actual tangent is not necessary. You know, it's not like as clear as would be a regular one. And the reason being is that one of the benefits that we have with cotangent is just that it's just going to shift the asymptote. But not to make it anything that's too new, I'll start with the tangent. The tangent actually, the only thing that was unique about the tangent, let's go ahead and draw your 3 lines so you can be ready to graph them. Oops, I don't like the way that line came out. I'll get it right. I'll get it right. Here we go. Okay. So let's do our 9 tick marks. And from here, one of the things that was unique about the tangent is that its period was different. If you remember, a period for a tangent function involved, like the frequency was 1, but it involved the equation pi over f, because values wouldn't repeat until you hit pi. And what was one of the things that resulted was this period of pi, and the scaling was affected in the sense that now we're going to be scaling by pi over 4. So we're going to reduce the values in which this gets graphed. This was still 1, 0, 1, and negative 1. It would still oscillate the same in a way. But we would now scale by 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and the last one being 8 pi over 4. Okay, so that was good. This is good in the sense that we have everything set up to just graph the tangent. Now, one of the unique things we found about the tangent was the fact that that one had asymptotes at the values like 2 pi over 4. And so it would happen after the first 2 tick marks. We would actually have an asymptote here. Now, actually, I want you to draw it just like this. Do not pass it. Don't go past it because, and there was another one here. Don't go past the top and middle. And the reason being is because this one, the cotangent, like once you represent it, all it's really going to do is going to shift the asymptote. So one of the things that we had, and don't draw this in, but I wanted to demonstrate it. A tangent would, after the asymptote, it would look like this. Don't draw this. Y'all remember that it would look like this in the middle? Okay. What's going to happen with the cotangent, because of the way the values work in the unit circle, the unit circle is going to now dictate in where the asymptote really should be at 0. You see this asymptote? Like imagine we're going to shift everything out. And the reason being is this. Let me show you. Let me give you proof. The cotangent at 0 degrees means I'm going to do the x over y, which means that this is x over y, right? So I'm going to do 1 over 0, which means that that's where the asymptote generates itself. What does it mean to us? It means that that at this value, at 0, at pi, let me see. Let me bring up my, here we go. So at 0, at pi. So you see the old asymptote line? Think about like if you're going to go through that. Draw your original tangent. If you go through it, you'll know exactly where the other new ones are at now. That's the reason I was saying that in essence, you could have thought about it independently. Just because the tangent function wasn't really necessary. Actually, those asymptotes don't really exist anymore, the ones we drew in that were in black. The ones that are important are the ones we did in red. And all that happened with the cotangent function is that it just moved the asymptotes. Instead of kind of just phase shift them in a way, just move them. Now the thing that I love about all this is that all this stuff is just add-ons. It's not like you're still going to do everything the same as far as frequency, oscillation, amplitude, starting point. Keep it all the same. But when you start graphing it, like when you graph it, then just place those two add-ons, those asymptotes and those inverses. I love it. Okay, let me go ahead and get the lights on and y'all can get started. I think you have like